if you've been looking at the algorithms that are available for solving steady-state CFD calculations, then you may have come across the pseudo transient approach. In this series of lecture talks, I'm going to be going through the pseudo transient approach in detail, and I'm going to be comparing it with a true transient approach and also with the method of using relaxation to stabilize steady-state CFD calculations. This is going to be a 3-part lecture series, and in part 1, which is this part of the talk, I'm going to be diving in and showing you the details of pseudo-transient calculations and how they're different to true transient calculations. So if this is a type of calculation that you've tried setting up before and you're interested in the detail and how it's different to other approaches and whether it's even appropriate to apply for your own case, this is definitely the talk for you. So let's jump into the talk and get started with pseudo-transient CFD. So the background for this talk is that in general, steady-state solvers in CFD are likely to diverge and they need some form of stabilization for us to be able to achieve a solution when we carry them out. And there are many different methods that we could use to stabilize a steady-state calculation. And one popular approach is to use relaxation or under-relaxation. And I've covered relaxation in a previous set of videos. And if you didn't catch that series, it's definitely well worth going back and watching the 3-part series that I did on relaxation, because it really provides a lot of the background for the pseudo-transient approach that we're going to look at here. And if you go back and watch those talks on relaxation, what you'll find is that the method of using relaxation to stabilize a steady-state calculation has some advantages, but it also has some limitations. And those main limitations are that we have to choose a relaxation factor, which I denote by alpha, and alpha can take any value between 0 and 1. And the difficulty with this is that the optimum value of relaxation that provides that balance between speed of solution and stabilization, it varies on a case-by-case basis. So it can be difficult to come up with a default set of values that are the optimum for a particular CFD case and that work for all CFD cases. And furthermore, every matrix equation that we solve in the steady-state solution process, so this will be the equations for u, v, and w, the 3 components of the momentum equation, k and epsilon, for example, if you're using the k-epsilon turbulence model, and an equation for pressure or a pressure correction, all of those equations have their own relaxation factor, and so we have a lot of different parameters that could be optimized, which makes it quite intensive and often means that the convergence that we achieve with the relaxation method is often not optimal, and convergence can be a bit slow. And of course for CFD our calculations are often very slow and we want to accelerate them as much as possible, and so perhaps there's a different approach that we can use to overcome some of these limitations of relaxation. And at the end of the last talk on relaxation, I briefly introduced the method of pseudo-transients as an alternative to using relaxation to achieve a steady-state solution in CFD. And the basis of the pseudo-transient approach is to add an artificial time derivative to the steady-state equation. And in equation 1 here on the slide, if you go back to the relaxation and CFD talks, you'll see the full derivation of this equation. But as an example, this is the steady-state energy equation for a single cell in the computational mesh. So this part is the steady-state equation, and what we do to stabilize the calculation is we add an artificial time derivative to that equation. And we add an artificial time derivative to all of the equations, one equation for each cell in the mesh. And it's that approach which allows us to stabilize the calculation, and that's what I'm going to be going through in today's talk. And so how does this work? We've added this artificial time derivative there, and what we do is we use the first order backwards Euler method, or the implicit Euler method, you'll sometimes see it referred to approximate that time derivative here as the difference in the temperature at the centroid of the cell between the current iteration and the previous iteration divided by the pseudo time step here, delta t. And if you substitute that into equation 2 for the derivative of temperature with time and rearrange, you find that we end up with this equation here, equation 4, which is the same form as the steady state energy equation we saw on the previous slide. We've got an AP, TP, plus a summation of the fluxes of energy from the temperatures of the cells that neighbour our current cell, and then we've got some source terms on the right hand side. But the difference here between the original steady state energy equation and the current one is we've modified the coefficient that's in front of TP. So we've got AP, which is the original, and then in addition we've got this artificial term which arises from the pseudo-time step, pseudo-time derivative, and then we've also got an additional source term on the right hand side there. And so this is one equation for a single cell in the mesh. If we repeat that process and add the time derivative to all of the cells in the mesh, we can then arrange in matrix form and we arrive at something that looks like this. And if you'd like a bit more detail, please, it's really well worth going back to that previous set of lectures that I did on relaxation and watching those through, because you'll see this in more detail. But how the matrix ends up is there's a modification to the diagonal terms here. So you've got A11, the diagonal term, and we've got this additional term which arises from our time derivative which we added, and then we've also got the additional contribution to the source term there. And the way the pseudo-transient approach stabilizes the calculation is that as we reduce the size of the artificial or pseudo-time step delta t, the magnitude of this diagonal term increases, and this increases the diagonal dominance of the A matrix, which stabilizes the calculation. So that's how it works. And this is why if you carry out a pseudo-transient approach yourself and you reduce the size of that pseudo-time step, you find that the equations become more stable, but they take more iterations to converge. And another way of thinking about this and how the pseudo-transient approach links with the relaxation approach is what we're doing here is we're specifying a constant pseudo-time step for all the cells in the mesh. And this is equivalent to actually having a relaxation parameter alpha that varies across the mesh. And the relationship between these two equations I derived in the previous set of lectures, but if you want the reference for how these terms are linked, you can look in the textbook by Ferziger and Peric, and you can find this on page 149 for yourselves. So the pseudo-transient approach is the opposite conceptually to the relaxation approach that we saw in the previous set of lecture series, where in the relaxation approach we have a constant value of alpha for all of the cells in the mesh and a variable pseudo-time step. But in the pseudo-time step approach we have it the other way round, where our pseudo-time step is constant, and that in effect is varying the relaxation coefficient across the mesh. So that was a quick background of the pseudo-transient approach and essentially what it does, and I covered that in more details in the previous talk. But in this talk, what I want to focus on is what's the difference between the pseudo-transient approach and a true transient approach, or an actual transient. And to understand the differences between these methods, we really need to think about the equations and the order that they're solved by the CFD code. And once again here, just for simplicity, I'm just using the example of the energy equation. There will of course be other equations solved by the CFD code, but it's easiest just to think in terms of the energy equation. And in the pseudo-transient approach, what we do is we have modified the steady state energy equation, so it's got the modification to the diagonal coefficient and the additional source term. And what we do is we just solve this equation sequentially several times. So we solve the equation once, we increment the pseudo-time step, and then we solve the equation again, increment the pseudo-time step, and repeat. And we solve the equation several times until the residuals have reduced sufficiently and all of the quantities that we're monitoring have converged, and that we have a steady state solution that doesn't vary in pseudo-time. So what we'll find is that as we get to our converged solution, moving to the next pseudo-time step and the next pseudo-time step doesn't change the solution, and so we have a converged steady state solution using the pseudo-transient approach. And how this will look is, if you look at the residual plot, it may look something like this, where the residuals initially start high and then they move around a bit, and then eventually the residuals come down and settle down to some value which is unchanging as you as you continue to iterate through the solution. And what this plot is telling us is that with a pseudo-transient approach, in the same way that when we had a relaxed approach to solving steady state equations, the solution is only converged at the end of the simulation. These intermediate or initial time steps are not converged. And that's going to be the key conceptual difference between the pseudo-transient approach and a true transient approach. Now, how is a true transient approach different to the pseudo-transient approach that we just looked at? Because both of these have a time derivative and both of these step through time. What's actually the difference? Because up until now, the only difference that we've seen is that we've just called by name that delta t, we've just called it pseudo-time step instead of time step. What is the actual difference? Because so far, the only difference we have is in the naming. Now, the difference is actually how we solve the equations in sequence. And in a true transient approach, if we were to choose a first order backward Euler scheme for that time derivative of temperature, we would have the same equation. And so we would solve our equation once during time step 1. And then what we would do is we would continue to iterate this equation within the time step. So we calculate additional iterations of the equation within the time step without incrementing to the next time step. And then, of course, when that equation is converged, we then move to the next time step, and then we iterate the equation again within the time step. And that's the key conceptual difference between a true transient and a pseudo-transient if both cases were to use a first order backward Euler approach. So how will this look on the residual plot? Now, many of you may have noticed this just by looking at residual plots for yourself, and the plot on the left is just an indication of what a pseudo-transient might look if you looked at the residuals. And of course the residuals start high and then they move around a bit and then they come down and eventually settle to some converged value. And what the residual plot is telling you, of course, is that the intermediate time steps, or the time steps before you achieve that converged solution, are not converged. So this red region here is clearly not converged. This is not a steady state solution that satisfies conservation of energy, but we have the converged solution at the end. Now, if you contrast that to a true transient approach, of course, the residual plots look very different and often they're very confusing, but they're likely to look something along the lines of this, where the residuals start high and then the residuals drop as we carry out those iterations of the equation within the time step. And then what we do is that after enough iterations, we find that the equations are sufficiently converged within a time step. And once that point is reached, we then move to the next time step. And you'll often see the residuals jump back up if you look at the residual plot. And so even though these residual plots on this slide are only indicative, they're actually showing you the difference between the two approaches. In the pseudo-transient approach, the intermediate solutions are not converged and only the final solution is converged, whereas with a true transient approach, the intermediate solutions are also converged. So this time step, we have a converged flow field. This time step, we have a converged flow field, and so on as we go through. So for you as the user of the CFD code, what does this tell you? Because ultimately you're trying to choose a method. You're probably not coding a CFD code for yourself. You're trying to choose a method for solving your equations. And the key conceptual difference to think about is, do you need the intermediate solutions to your simulation? Are you just trying to start from an initial condition and you only care about the final simulation which conserves mass, momentum and energy and doesn't change as you iterate more? Then you can get away with a pseudo-transient approach, because those intermediate solutions don't matter and you don't care about them. You're only looking at that final solution. But if you do need the intermediate solution, for example, if you're looking at the evolution of a quantity or the flow field with time, you care about the solution at every single time step, and each of those needs to be converged. And if that's the case, then you would need to choose a true transient approach, or in a CFD code, it will just be called transient. And An interesting point to note here, of course, is that you could use a true transient solver to get a steady state solution. If you load up your simulation and you choose transient and then you iterate through time for a long time and you can step through time, eventually you'll reach a position where your simulation doesn't change, or it changes by a very small amount, and that would indicate to you that you have a steady state solution and you have reached it with a true transient. But what you may have noticed here is that that approach is a lot slower because you're having to put in extra effort to converge those intermediate time steps, and you're iterating within the time step, which is ultimately not a very efficient way of getting to a steady state solution. So what we've discussed so far is you may have noticed that there's some difference in the speed of the calculation and how long it's going to take, where you could in principle use that true transient approach to get your steady state solution. But what we're trying to do here is we're trying to accelerate and get things in fewer iterations. We want to take as large time steps as possible. We don't really care about converging the simulation properly until right at the end. We're just trying to aggressively step through time to achieve that steady state solution as fast as we can without diverging along the way. And an interesting consequence of this comes when you have a simulation with multiple domains. So when you have multiple regions of fluids and different solids all connected to each other, and you're trying to advance the solution in all of those domains together, then there are some further interesting implications for how you might achieve a steady state solution in these kind of domains. And the example I want to use to just illustrate this to you is just a simple example of the flow of air inside a concrete pipe or duct with a thick wall. And really the choice of concrete and air is not essential here. You could have concrete and water. The main difference is you've got two different domains with quite different material or physical properties to them. So you've got a simple pipe, you've got air flowing through the middle of the pipe, and of course the air will form some kind of profile where its velocity is 0 at the wall and higher at the center line of the pipe. And the air that's moving inside the pipe is hot. You've got some hot air within the pipe, and of course this is going to heat up the concrete liner surrounding the pipe, and because the pipe is then hotter than the ambient, you're going to get some natural convection cooling the pipe. So you're going to have some buoyancy driven flows above the pipe. And this is a fairly typical example that does occur in some areas of engineering where you've got a fluid region flowing within a solid region with different material properties. And what we would like to do here is we'd like to set up a steady state solution that steps through as fast as possible and achieves a steady state solution for the temperature profile in the air and the solid, and also the velocity profile in the air, of course. And we want that situation where nothing is changing with time or with iteration. We want that steady state solution. And if we think about this problem conceptually and with the properties of air and concrete, and if you look this up either online or in your favorite textbook, what you'll see is that the concrete has a much higher specific heat capacity than the air, Cp. So what does that mean physically? What does that mean? It has a different material property. What does it mean? It means that the concrete takes more time to heat up than the air does. And for this particular situation, what you'll find is that the air heats up very, very quickly. If you were to iterate this through time in a transient solution, the air heats up very, very quickly, whereas the concrete takes a long time for its temperature to respond to changes in energy flux passing through it. And this is going to cause some problems for our steady state simulation because we don't really care about these intermediate times where the air and the concrete are heating up. We want to just as fast as possible get to this final solution where we have the temperature distribution in the air and the concrete and everything balances. But straight away what we can see here is just looking at this time axis is that the concrete is going to be slowing us down. If we were only considering the air, we'd get there quite quickly. With a pseudo transient or a true transient approach, we'd arrive at this final solution here where the air temperature is not changing. We'd get there very quickly. But with the concrete, it's going to take us a lot longer to get there. And this isn't great. We'd like to speed up our CFD simulation and try and get through time and get to that final solution as fast as possible. Now, a massive advantage of the pseudo-transient approach is that because we don't care about those intermediate solutions, remember we throw them away and we're just jumping through time as fast as we can, not properly converging until we get to that final solution. And what that means is that we can use different time steps in different domains in the CFD code. So we can use a much larger time step in the concrete than we do in the air. And so just looking on this graph, you could see that after 1, 2, 3, 4, 5, 6, 7 or 8 of whatever these delta T2 time steps are, our air temperature is going to be no longer changing. But then in the concrete, again, after 1, 2, 3, 4, 5, 6, maybe 7 of the delta T1 time steps, the concrete has also reached its final temperature. And of course, these intermediate solutions will not be correct. They won't conserve mass, momentum, and energy. But that's okay, because all we care about is getting to this final solution as fast as possible. And so that is a massive advantage of the pseudo-transient approach, which again we don't get in a true transient approach, because when we do a true transient, we increment by a time step, delta t, which is the same in both domains. It will be the same in the air and the same in the concrete, and we converge within that time step so that at a certain time, energy and mass and momentum are conserved, and then we move to the next time step, and again, energy, mass, and momentum are conserved. And so this is another way why the pseudo-transient approach gives us a speed up over the true transient when we're just trying to reach that steady state solution. We don't care about the intermediate solutions, and we can jump through time with different time steps in different domains. So if you had multiple domains, you might have water, air, concrete, and steel. You could have different time steps in all of those domains in the pseudo-transient approach. And so this leads us to the final question of the pseudo-transient approach, and the most important question is, what is that pseudo time step size going to be? Because in a true transient approach, we pick a time step that's going to be small enough for us to resolve the evolution of the solution through our entire simulation, and we make sure that that time step is small enough for our calculation to remain stable. But this is going to be more difficult for the pseudo-transient approach, because we're having to choose different time steps in different domains, and we want them to be as large as possible for us to have a fast solution, but we don't want them to be too large because our steady state calculation again is prone to divergence. If we make that time step too large, remember back to the matrices that we looked at the start of the talk, the diagonal coefficient on the A matrix won't be as large if our delta t is large. So we need some method of choosing the pseudo time step size, and that's the most important aspect of our pseudo transient approach. This replaces choosing the value of alpha for the relaxation approach. We're not choosing alpha anymore. We need to choose delta t in each of the domains. And just to recap a few of those points, what we want to do is we want delta t1, delta t2, delta t3 for all of our domains. We want to choose it so that the steady state solution is reached in as few iterations as possible, and we want to make sure that the calculation doesn't diverge along the way. And the thing to think about when choosing this pseudo time step size is actually quite different to the method of choosing the relaxation parameter alpha. And you'll remember, if you have watched my 3-part series on relaxation, that essentially what you have to do is you start with the default values of alpha for each of your equations, and then you can use a bit of trial and error to find what the optimum value of alpha is for each equation. But an advantage of the pseudo-transient approach is that we don't have to do that with delta t in each of the domains. We don't have to start with a default and then use trial and error. We can actually use the physical properties of the domain we're looking at to get a good estimate of what an appropriate pseudo time step size would be. So this is another massive advantage of the pseudo-transient approach, is that our method of achieving the steady state solution is based on something other than trial and error. We can get a good guess of what delta t should be, and in a matter of fact, the CFD code can often calculate this automatically for us. So you're taking less of the control from the user and you're putting more of it on the CFD code. And the reason why that's important is if you think about a steady state solution to a typical problem. So, for example, you could have the steady state flow over the back of an aerofoil where the flow comes in and the pressure distribution changes around the aerofoil, and this gives rise to lift and drag. Or if you think of the flow in a lid-driven cavity where the top of a cavity is moving from left to right, and this is driving a swirling motion within the cavity. Under steady state conditions, we expect these solutions to be unchanging with time. They are eternal. As we increment through time, regardless of the time step, the solution should be unchanging. And so when the user approaches the CFD code, they will look at the case of flow over an aerofoil or a cavity, and they should not need to know what time step we need to achieve the solution, because they just want the steady state converged final solution where everything balances. Why should the user need to care about how we increment up to that solution? This should be handled automatically by the CFD code. And the lid-driven cavity flow is an easy example of that, because we don't know how we should achieve this solution numerically. We just know that eventually the lid should be moving and the flow should be stirring and moving around at a constant rate. And so this pseudo time step size should be calculated automatically by the CFD code. We don't want to have to do what we do with relaxation and give the user control over 10 different values of alpha. And so how could the CFD code calculate this pseudo time step size automatically? Well, the trick is to notice that we expect it to be based on some form of the material properties of the domain. Something about the domain itself that we're solving should be able to tell the CFD code what the pseudo time step size should be. And just as a first example, if you consider the flow over a backward facing step, like in case 1 you can see here on the slide, where the flow comes in from an inlet and then it separates off the back of a step and then exits the domain at the right hand side. Now if you consider an identical case here with case 2, but the domain has just been extended and is a lot longer, which of these cases do you think would take longer to converge if you were attempting a solution? And the trick to think about this is imagine that case 2 was extended a really long way. Which of these numerically do you think would be quicker to converge? And another example you can think about is what if you took the same backward facing step flow with an inlet velocity of 1 meter per second, but this time you change the velocity to 5 meters per second. Which of these two cases do you think would actually converge faster? And just thinking about this is immediately going to give you some insight into how the pseudo time step size should be calculated automatically by the CFD code. And hopefully what this thinking has brought you to the conclusion is that what's going to be controlling the speed of the convergence of this calculation is going to be the time taken for the effect of boundaries to propagate across the domain. Now in this case, if you think of this inlet here where we've got a velocity inlet on the left hand side at some speed, then after 2 seconds we may have a velocity profile developing here in the domain, and then after 4 seconds here, and all the way through until the outlet of the domain taking about 10 seconds, for example. It's taken 10 seconds for the effect of this boundary to propagate through the initially stationary domain until it reaches the outlet. And it's this time that's really going to take control the overall time needed for us to converge that simulation. We expect something around 10 seconds maybe, say, for this solution to be converged to a steady state condition. So it's going to be something related to the time for the boundary to propagate across the domain. And what we could use for the pseudo time step is once we've got an idea of how long it takes the effect of the boundary to propagate, in this case all the way across the domain, we could take a fraction of this time, and that would be a good choice for the pseudo time step. So for this case, for example, if we took 1/100th of the 10 seconds it would take the effect of this boundary to propagate across the domain, then our pseudo time step size would be 0.1 seconds. And so we could say I'm going to do 100 iterations with a pseudo time step size of 0.1 seconds, and over that simulation we'd expect the effect of this boundary to slowly propagate across the domain, and by the time that had fully propagated across the domain, and maybe some other effects may have happened as well, we'd expect our residuals to have come down and our solution to achieve a steady state energy balance, or in this case, momentum balance. So this is going to be the key for us in setting up a pseudo-transient simulation. We want to estimate the propagation time. We want to have some kind of estimate about how long it's going to take the effect of boundaries to propagate across the domain, and then we can take a fraction of this, and that will be our pseudo time step size. So how's our CFD code going to do this? Well, if we just think of from dimensional analysis, we want to get a time, and an easy way to calculate it would be to take some characteristic length of the CFD domain itself. So not the cells in the mesh. If you think of the entire CFD solution domain together as a unit, if you think of some characteristic length for this shape, maybe that's the length from one end to the other, or maybe it's the square root of the area, that would be your length. And then if you knew the characteristic speed, in this case the speed at the inlet might be a good idea, you could divide one by the other, and that would give you a characteristic time, or how long it would take this boundary effect to propagate across the domain. And you could do this in different ways in different CFD and different parts of the CFD domain. So you could do the same thing in the air region of our air concrete pipe, for example. We'd know the speed that the fluid is moving, that would be the U0 in the air, and then maybe the speed that the heat is moving through the concrete, and then we could calculate the characteristic length from one end to the other, and that would give us different characteristic times in the air and the concrete, and we could take a fraction of each of those, which would give us those pseudo time steps that we need in the different domains. So hopefully just from thinking about this, you can see that if the speed that boundary effects propagate across the domain is different in different domains, maybe you had different densities, for example, or different physical fluids or solids, then you could use this to work out roughly what a good pseudo time step size would be in each of the domains. And that is going to be the principle of the pseudo transient approach. And I just wanted to do a quick recap at this point and do a comparison of the pseudo time step size versus the relaxation. Maybe so far in this talk we haven't gone into too much detail about how exactly we choose the pseudo time step size, but hopefully you've noticed that the pseudo time step size is in some way based on the physical properties of the domain that we're looking at. So a pseudo time step in air is going to be very different to a pseudo time step in concrete. And this is fantastic because this allows the specification of our numerical algorithm to be different for different cases and give us that case-by-case basis variation. And this is very different to the relaxation approach, where we may, for example, just specify a value of alpha of 0.7, and that would be the same in the concrete and the air. And this is just one of the many reasons why the pseudo-transient approach is better in principle to relaxation when you're wanting to achieve that steady state solution. But of course, in part one of this talk, I haven't managed to address all of the questions around here. You probably still have some questions for the pseudo-transient approach, like how do we calculate this characteristic length for different domains? Because often CFD domains have a very complicated shape, they have very complex internal and external structures. And how do we calculate U0? How do we calculate the speed that boundary effect propagates across the domain? Because that can be quite complicated, and we need something automatic, so we need a very robust algorithm for specifying what U0 and L0 might be. And these questions I'm going to go through in part 2 and part 3 of this lecture series. So by the end, everything will be wrapped up and you'll have a great idea of how the pseudo-transient approach actually works and how these parameters are calculated automatically. So just to wrap up, I really want to emphasize that the pseudo-transient approach is a tool to achieve a steady state solution. It's very different to a true transient approach, because in a true transient approach, we also have to converge the intermediate time steps, or the time history. And we don't need to do that in the pseudo-transient approach because we're just jumping through time and we're trying to get to a steady state solution as fast as possible. Now, the main advantage of this approach, of course, is that because we don't care about those intermediate time steps and they don't really need to satisfy conservation of mass, momentum, and energy as long as they don't diverge, it means we can have different pseudo-time step sizes in solid and fluid domains, and that means we can accelerate the calculation by using larger time steps in domains that take longer to converge. And these are typically solids with high specific heat capacity, and that's one of the things you'll notice if you do a lot of conjugate heat transfer simulations. So that brings me to the end of part 1 of my lecture series on pseudo transients in CFD. Let me know in the comment section, did you find this talk useful? Do you think you finally understand the difference between pseudo transients and true transients and relaxation, and how these methods differ when you're solving steady state CFD calculations? I'm really hoping this talk has helped clarify these often confusing approaches to you and that you've now got a good idea of what the differences are. So yeah, let me know in the comment section, let me know how you found it and if this talk was useful for you. And coming up in part 2, it's definitely worth sticking around for part 2 and part 3 of this lecture series, because I'm going to be going through the automatic calculation of the characteristic length scale and characteristic speed, and you're going to see how this is different in CFD domains that have different flow physics, like compressible flows and creeping flows, for example, and how the CFD code accounts for all of these. And you're also going to get a good idea about what the timescale factor, or the solid timescale factor and the fluid timescale factor are, because these are options that are often given to you as a user of a CFD code. So if you're using a pseudo-transient approach or considering using it, definitely worth sticking around for part 2, because you're going to get a good idea about what these user parameters actually mean when you enter them in your code. So until next time, thank you all very much for watching and supporting the channel. I really appreciate it, and I'll see you in the next video.